Hello, everybody. Welcome back. This is another Q&A with Dr. J. Dunn of My Happy Genes. We're going to tell you the 8 common misunderstandings about DNA testing. Dr. J has a list, and she's the expert here, so take it away.
Thanks, GC. It's good to see you.
Good to see you too.
I get a lot of questions from people, and there's a lot of misinformation out there, or misunderstandings, I should say, misconceptions about genetic testing. So I just wanted to answer some of those that people have written in about. And then the first one is that a lot of people are afraid to get their genes tested because they think that's their destiny. They don't want to know how they're going to die. They don't know that they are at risk for heart disease or cognitive decline or whatever it is. But that's not true. Our genes are our genes, yeah, and you've heard us say that on this series, but you can do a lot to modify the risks through proper diet and lifestyle and supplements. You can modify the enzymes that are coded by your genes that are at risk. And I think we've talked about this quite a bit, but I want people to know that we wouldn't be doing this if that was the case. I'm not interested in testing people's genes, but if there's something we can do about it to modify the risk, then that is a really good reason to get your genes tested, at least in my.
Absolutely.
And the second one is that your genes will change over time. And I've heard many people talk about this. You can change your genes. You can turn them on, you can turn them off, you can modify how they are, or what you've inherited. But unfortunately, that's not. Your genes are pretty much, like I say, you inherited what you inherited. Your eyes are not going to turn from blue to brown. Your hair is not going to instantly go red. That just doesn't happen. And the same happens for the genes that are in your body that are coding for certain enzyme functions that we've been talking about. Those genes are not going to change. They're written in stone, but that doesn't mean that the enzymes that they code for can't change, and they can very much. And again, ties right back into that first misconception that the enzymes are what we can work with, and we use nutrients to turn them up, dial them up, essentially, make up for genetic variants. And so that's where we can make a difference in the genetics.
So there's no reason to get your genes tested again after being on a protocol.
Exactly. And that's one of the next ones. So that's number 3 is, do I have to get my genes retested? And it's no, you never do. We test for 675,000 SNPs, and there are more SNPs. You could get your whole genome tested, but it's really not going to do you a whole lot of good unless you're looking for different things than how to work with your health. Because there are only certain genes that we know about and that meet our criteria for putting in our reports. And that is that there's some science behind the fact that they are associated with a certain risk. Number 2, that there are ways to modify what those genes do in the body. Can we use a cofactor, a coenzyme, to change the expression of the enzymes that they code for? And number 3, that there's good science behind that and good clinical evidence that does work, that the outcome does change. Does that make sense, or was that overly
Yeah,
clear?
no,
Okay.
absolutely. When you get your whole genome tested, science hasn't even made sense of what all those numbers mean.
Yeah, that's exactly right. And there's a lot of missense kind of stuff in there and introns, spaces between the genes that we don't have any idea what they really mean. And they really don't code for enzymes in the body. It doesn't really pay. It doesn't mean that the more the merrier in the genes. However, that being said, when we used to use Ancestry and 23andMe's raw data, they tested for like 40,000 SNPs. They were missing some of the critical ones that we were looking at, which was the ones that kind of govern our physiology and how our body absorbs nutrients, or how we make neurotransmitters, or how we detox. They were looking at ancestry genes. So the set of genes that they tested for was very different than what we were looking for. So in that case, size doesn't necessarily matter. What's in there does matter. So what's coded for. And then the difference between a mutation and a variation, or a SNP, and maybe you've heard me talk about a single nucleotide polymorphism, which is just a one base pair change in the gene code that makes for a variation. And variations are nature's way of playing with different options. Let's make this person have bigger muscles and this person has smaller muscles. Which one's going to survive better in these conditions that they're in? This person holds on to weight better. This person has a higher metabolism. who's going to survive during times of starvation? It's going to be the person who holds on to weight. So nature plays with variations to its natural selection versus a mutation, which is a damage to the DNA, which can occur from chemicals and pesticides, radiation, heavy metals, electromagnetic fields can all damage the DNA. And we have repair mechanisms and in place to put those pieces back together. You can have breaks in the DNA. You can have all kinds like just disappearing of a DNA strand. That's not uncommon. So we have ways to repair that damage, and that's largely due to methylation. So it's another reason why methylation is so important, is that with all the damage that we're exposed to, much more ways that we can get damaged, our DNA can get damaged now than our ancestors had to deal with. So it's a good thing that we have methylation in place properly. But if you have methylation variants, then that DNA damage can't be repaired thoroughly. So it's just another good reason to look at your methylation pathways and make sure they're optimized for repair. Some genes are indicative of a particular disease. There are definite genetic variants that doctors look for to diagnose something like cystic fibrosis or Tay-Sachs disease, as we mentioned. Those kind of diseases are definitely one gene, one disease, and that's the exception to the rule. Those are the exception to the rule that we've talked about, which is that it's many different genes that contribute to a disease process. And things like birth defects are also, they can be due to the mother's diet and lifestyles that can allow genes to express that wouldn't normally express if they were methylating properly. So that's one case where methylation changes the outcome of a gene turning on and off for the rest of their life. And that brings up the last one, which is that genes turn on and turn off. And yes, in some sense they do. And in that case, what I just mentioned, imagine that you have a gene for cancer and your mother took a bunch of methyl groups during pregnancy, or she was methylating properly, or she was eating a healthy diet so that methylation was optimal. Methylation is the little tiny molecule that turns off a gene during the embryonic development. So what does that mean? That means that gene is there. It's not like it disappeared. It's there, that gene that could have caused cancer. But because the methylation pattern was set in gestation, then that gene will never turn on during that child's lifetime. So that's a pretty cool concept. That's a really incredibly beneficial reason for getting your genes tested and getting optimized during pregnancy, especially, or before, actually, before,
Mm-hmm.
so that your genes are optimized, your methylation is optimized to turn off some of these genes that could potentially cause diabetes and heart disease and cancers down the line. Usually, when I talk to people or when I work on people that are super healthy, I go, why? Their genes don't look any really different than somebody who's got a lot of health issues, but it's usually when I ask them about, tell me about the health of your mother when you were pregnant. And they're like, oh, she ate really well and she took a lot of supplements and she didn't stress out. And it made a huge difference. You can really tell. Those people that their mothers ate a very bad diet and they didn't get proper nutrients or they were under a lot of stress and trauma, it affects that child for the rest of their lives. And it's through what we call these methylation patterns where the methyl group is set down before we're born to tell our bodies this is the environment that you're going to be born into. These are the genes we need turned on and turned off. It makes a huge difference.
So if this child who had inherited these genes from the mother who had poor lifestyle, stress, whatever, can they not also get their genes tested, see those markers of risk, and do what we tell everybody to do and not get the outcome of
Yes,
cancer?
yes, but you have to
Okay.
stay on it. Yeah, for the ones that were born with those epigenetic markers or the methylation markers in place, they don't have to struggle with it like those of us whose parents, like my parents, were big drinkers and smokers, and they didn't really particularly have a good diet. So I've always had to struggle. My genes were more expressive because they weren't turned off essentially during gestation, and where other people had a much better outcome or a much better pregnancy. Their parents had a much better pregnancy.
Okay. So there, you may have a bumpy road, but you don't necessarily end up with the disease if you take action.
Yeah. Can I show you I want to show you a study done by agouti mice.
Sure. I love
Can we do
agouti
that?
mice. I feel bad for them, but I love
Okay.
them.
I know. Poor things.
People are like, why does she love
Oh,
agouti mice? What the hell is an agouti mouse?
okay. So you can see these two mice are genetically identical and they're the same age. They are basically clones. So while pregnant, both of their mothers were fed bisphenol A or BPA as plastics, but different diets. The mother of this mouse on the left received a normal mouse diet. The mother of the mouse on the right received a diet supplemented with choline, folic acid, betaine, and B12. Those are methyl donors, right? On the right, you can see that the yellow one is going to be prone to obese, cancer, and diabetes for the rest of its life. It's going to have to fight against those things. And the one all the way on the right, the methyl groups are in place there in the DNA, and it stays thin and healthy and doesn't have a lot of the problems that the rest of us that have unhealthy mothers have to struggle with. So
Mm,
does that make sense?
yeah,
It's like those
absolutely.
are,
That's a great visual for the whole
yeah.
thing. Yeah.
So it's super important if you're pregnant, if you're thinking about getting pregnant. We segued into that from the 8 reasons, the misunderstandings, but it's an important topic because it's one of the misunderstandings is that your genes are written in stone. Yeah, they are, but there are ways to have them express or not express, and that was my point with that.
Very good explanation. And I think that those are eight. They sound common to me because I was that one who was afraid to get my genes tested because my mother had cancer, my father died at 27. But once I did, I realized it's like any other kind of information. It's like not wanting to get on the scale.
I
But
know.
it's a lot less painful than getting on the scale for most of us most days. I would say if you have been thinking about getting your genes tested, but fear is the reason that you're not, this whole episode should have helped you get over that fear and see the value, especially with the methyl groups, because maybe you're not going to be pregnant, you don't want to be your past pregnancy, but methylation can still help with other things. It's not
Yeah,
like it's only for that period of life.
and I would encourage you to go back and look at the Q&A that we did on methylation if
Yep.
you're interested in more of that.
Yeah. All right, people, we will be back again next week with another Q&A with Dr. J and GC. Thanks, Dr.
Good to
J.
see.